So,
And
go ahead.
the
Camera is here.
okay. So hello everyone. Good evening. I know this is very late hour to be talking about some theoretical concepts, and also we heard already about quantum dots from Tomáš Novotný, but I would nevertheless like to present some of the research that I've done during my PhD in the Prague condensed matter theory group. How do I switch? Oh, right, it's working already. Okay, so our system of interest is the quantum dot coupled to superconducting leads, and I'm sorry, one more thing, I don't have, I'm not seeing time here, so maybe.
Time?
Yeah, so.
Yes, you have 30 minutes.
Tady
máš, že je někde začátek toho. Aha, není.
Okay, so.
Dobře.
Okay, so our system of interest is the quantum dot coupled to superconducting leads, where by quantum dot I mean a system with discrete quantum levels, more specifically a system where we can just pick one energy level and study that, and there can be up to 2 electrons on this quantum dot energy level, which have which can interact with Coulomb interaction, which is what makes the system complicated. Okay, such a system is quite tunable. The experimentalists are able to tune the energy level of the quantum dot, and perhaps even the superconducting phase difference, which governs the transport, the Josephson current and the transport from one lead to another. One practical example of realizing such quantum dot systems is with carbon nanotubes, as done in laboratory of physics in Orsay. Okay, so I will skip real quick through some of the introduction because Tomáš Novotný already talked about that today, and I will go to results. Nevertheless, to remind you a little bit of non-superconducting quantum dots. As I've said, it's a system with discrete energy levels, so electrons can tunnel from one lead to another through the dot. And theoretically, there are 2 main models to describe it since the 60s. We are starting basically from the single impurity Bresson model. Sorry about being real big here. What I just want to introduce is the Kondo effect, which is an anomalous low temperature quantum effect, which leads to an anomalous rise in conductance of the quantum dot, and to current flowing in energy ranges that would be otherwise blocked. The Kondo effect has a very special property called Kondo universality, which is that experimental data or physical quantities which would, depending on the system's parameters, which would be very different, fall on one single curve, if the temperature is rescaled by this, this is called Kondo temperature, TK. So the Kondo temperature is a scale that is exponential in U over gamma, the Coulomb interaction over the lead coupling, and it leads to this interesting property of that at certain temperature ranges, all physics basically only depends on this scale. Okay, so as you can see, the quantum dot is a very difficult system to solve already in the non-superconducting case. What we usually do is, what people do is use numerical methods such as the numerical renormalization group, which however still on today's computers takes hours to compute 1 point or so. And now we even add some superconductivity into it. I believe I don't have to introduce the Josephson effect to this audience. If there is superconducting phase difference across the junction, then we get some Josephson current flowing. The only thing I want to say is the first Josephson relation, the current phase relation, which was derived for a planar Josephson junction. It's well, there is still quantum transport in more complicated systems, but it's not this sinus anymore. It's not it's not the sinusoidal dependence anymore. Okay, so now to the superconducting quantum dot. So as I said, there is this basic impurity physics, there is Josephson transport physics. In the DC setup, this is a hard problem. In the AC setup, this is basically unsolved, not solvable with today's methods. So let me introduce the Hamiltonian. We have 3 parts describing the dot, describing the leads, and describing the coupling between the dot and the leads. The dot is described by basically 2 parameters, the level energy and the Coulomb interaction of the electrons on the dot. We have the lead part. This is Fermi basic metallic lead, and the superconducting part with the gap size delta. I believe we assume that delta is same for both of those superconducting leads. And then we have the tunneling part, where basically we assume that gamma, it's the same, where we assume that the tunnel coupling can be set as a constant, which is this gamma, as a constant in the energy range of interest. Okay, and then there is one more parameter, which I will be dealing with today. It's this coupling asymmetry, which is the ratio between gamma left to gamma right, or the other way around, it doesn't matter. But let's say gamma left to gamma right. And yeah, people have, in the past, people tended to kind of ignore this asymmetry parameter because because it's hard for theorists to calculate all asymmetric systems, and experimentalists perhaps weren't sure about their setups. But we have found a way to describe it, its theoretical effect. And I skip some of the phenomenology of this system, or really quick with this quantum dot, like the system is not solved exactly, but we know some of its features. We know that inside the superconducting gaps, there are subgap states, so-called Andreev bound states. And we know that when these can be observed in SEM, and we know that if they are crossing, there is a quantum phase transition in the dot. And this quantum phase transition is called the zero pi transition, and it leads at zero temperature in theory. There is a jump in the supercurrent. In finite temperature, it's not so clearly visible, but there is still change. Okay, phase diagram. Good. So I wanted to talk about the asymmetry today. Basically, to remind you, we have this coupling to the leads, gamma left, gamma right. We have this superconducting phase difference, which is governing transport across the junction. And then we have an asymmetry parameter between gamma left, gamma right coupling. And what I want to show now is that there is an equivalence in the physical description between the symmetric system and asymmetric system. So we start with the non-interacting Green's function. Don't worry if you're not familiar with the formalism, it's just another equivalent description of the system. And what is interesting to notice is that the superconducting phases phi only enter this Green's function through this factor, which is frequency independent. By frequency independence, I mean it doesn't depend on these omegas. And so we can play with this factor. And you will agree that if this stays a constant, then the Green's function stays constant and the physics stays constant.
So this is the superposition of two states, right? From left to right. This sum. Can you say like that? Because like gamma.
I don't think I can say that. No, it's
Should just some complex numbers.
No, but look.
seriously. Yes, so we take this.
Just the transit function of the quantum dot between square.
It's no, it's I don't think the Green's function has such an easy physical interpretation to be able to say this is hopping. This is like sum of two hoppings. Maybe it's
No, because what is
can
on the
be
left
said,
the
but-
bulk in the function. I know this. I'm a mouse. Okay, anyway.
Anyway. So yeah, so we agreed that this factor, if it stays constant, then the Green's function is staying constant. Do you mind? So we can just write this factor in amplitude and phase notation, because as you said, it's just a complex number. And now there is also a notion called, sorry, I keep clicking that, called gauge invariance, which says that basically Josephson transport is just depends on the phase difference of these two phases, and in the Green's function language, it translates into being able to transform away this complex exponential. So basically, if we can make the real part of this number constant, then we are keeping the physics of on-dot quantities. And that's exactly what we do. We introduce a substitution. We say, okay, we have some asymmetric system with some superconducting phase difference. And we equate it, we find an equivalent system with the same gamma without asymmetry and with an effective phase difference corresponding to this asymmetric system of ours. And that is basically the symmetry-asymmetry relation, which allows us to calculate the properties of asymmetric systems from the properties of a symmetric one. Now you can say, but wait, we've started with the non-interacting Green's function, right? So we neglected this Coulomb interaction U, which is what makes the problem problematic. Otherwise, we could solve it basically exactly. And that's a trick that maybe some of theorists may want to remember, that actually the full Green's function, however complicated and however difficult to derive, is a functional of this G0, of this non-interacting Green's function and the interaction strength. So if there is a symmetry in this G0, in this non-interacting Green's function, through it being a functional, it carries over to the interacting case. And that's our conclusion, that this relation is valid. So to show you some implication, basically, if you have an on-dot quantity, anything that can be computed just from the dot Green's function, you can spare yourself the numerics. If you observe the blue curve on the left, then that's the symmetric case, and all the red curves are asymmetric cases derived from this symmetric one, and going through, you can see they fit the more exact numerical renormalization group data. Again, computing any one of these renormalization group points can take a few hours, so this is a significant help. So with the phase bound, so this is most easily applied to the phase boundary. It's just this phi I substitution. Then on-dot quantities are also just this substitution. The Josephson current is slightly more complicated. Why is the Josephson current more complicated? It's because the leads enter the theory. The Josephson current can't be fully derived just from the on-dot Green's function. The leads are important. And when we know this, then my gauge invariance arguments that we can transform this factor over here again, it's not quite valid, and we have to treat it properly, and I've done that in my thesis, and that's one way to derive this formula for relating the symmetric and asymmetric Josephson current, which you see is a bit more complicated. But actually, if you look at what this prefactor is, then it's also just the derivative of this composed, of this substitution factor inside the Josephson current. So that's because we can also get the Josephson current as the derivative of free energy, which is a quantity on the dot. Yeah. Okay, so I have 8 minutes. So let me not go through the application to experiment and instead tell you some implication for the notion of Kondo universality in these superconducting quantum dots. So what people have believed, I told you about this universality in Kondo universality in non-superconducting quantum dots, right? So the fact that the properties only depends on this TK, on this Kondo temperature scale. Well, in the superconducting case, obviously you have one other important scale, which is the superconducting gap delta. So people have long believed that the ratio delta over TK is the only governing parameter in this low temperature physics in a certain in the Kondo regime of the quantum dot. But we say, oh no, but the coupling asymmetry is important here. It can shift the phase boundaries significantly and just alter the physics. And but then we took a closer look, and actually we realized that we can use this real part of the factor that I was showing before, this chi, to restore a universal dependence in some sense. That there is, here you can see we plot this superconducting gap over TK dependence, and here we plot this chi function, which is dependent on the phase difference and the asymmetry. And for very different U over gamma ratios, 15, 20, so deep in the Kondo regime, but very different, we got one curve, one curve that we fit it to be an exponential. There's some kind of Kondo universality in that this is for the phase boundary, in that we can, for different U over gamma ratios, find out the position of the phase boundary from this simple exponential formula. This formula doesn't contain the level energy explicitly, so this check is done in this picture. We basically check the validity of this formula in depending on the level energy, and you can see the position of the phase boundary stays constant for quite a long time until basically we are with this well, this parameter is basically epsilon. Oh, right. When the epsilon becomes comparable to the Coulomb interaction, then we are getting out of the regime where we would expect the validity of this universal scaling. So anywhere where TK is a relevant scale, this formula also holds independently of the level energy. And that's all from me about this asymmetry. We hope to have convinced the experimental groups over the years that the asymmetry is a parameter to check out for. We have given formulas which can which relates the symmetric and asymmetric cases for different quantities. And we have given a simple formula for the position of the phase boundary in the Kondo regime of the superconducting quantum dot. Thank you.
Okay, that's great. So let us have a seat, take a seat.
Yeah.
So there was already one question
There
from the
was a
audience, which so Bani, could you go ahead with your question? Bani, can you hear us?
Yeah.
Go ahead.
Hi, Asweta.
Hello.
Yeah, so I have two questions actually. One is technical. So how do you
Sorry,
decide-
I'm having trouble hearing you.
now? Can you?
Yes, if you speak aloud.
Okay.
Yes.
So how do you decide which U values to choose for energy calculations?
You mean
Yes,
like
yes.
here?
Yeah.
Yeah, we just took two different ratios, which were very clearly in the Kondo regime and very clearly different. And we did a check because the energy precision depends on how you select the width of the band, right?
Yes.
So D is the discretization bandwidth. So we just checked that our precision is correct for this U over gamma 15.
I see.
Yeah.
Okay, and the second is, I mean, just to understand better. So you said that this asymmetry which you see for the non-interacting Green's function should also map for the interacting Green's function. So yeah, so basically, I don't know. So it means that if I just try to do this with Dyson equation, it really exactly maps, or what happens?
Dyson equation, yeah, basically, I think from the Dyson equation, you can somehow see that this interacting Green's function is a functional of G naught and U, right? There are no other quantities
Definitely, yeah,
entering,
definitely.
yeah. So we are not doing any actual calculation. The claim is G naught has a symmetry. Yeah,
Yes.
you can do a substitution in G naught, and G naught stays the same. And
But
if
then
G
your
naught
Dyson
stays the same,
equation, you are expanding, right, in power sub G naught. You will have G naught
yeah.
squared to the power n. So then your symmetry will also obey, like that it will also obey when you go to your higher order G naught.
Didn't quite understand, but yes, the claim is if G naught has the symmetry, then G will also have the symmetry.
I see.
Because it's just the substitution inside G naught, you know? So it's just the substitution that keeps G naught constant.
Okay.
So perhaps this trick comes handy sometimes.
It's just a question. I don't know. It's very interesting, but I was just curious. Like,
Yeah, sure.
Thank you.
I'm glad you asked. Okay.
All right. Thank you for those questions. Do we have any more questions from the audience?
Okay.
So just come here.
So my question, I mean, this is nobody hearing. Basically, the question is to the first equation, yes. I mean, because we've got let's say
The factor here.
but this is not a mathematical, let's say.
Yes, this is mathematical equality.
Yes, I understand, but what are the physical explanation of those signs? I mean, the x and this is a
This is chi.
Chi.
And this is psi.
Psi, but psi, it's what kind of the function is this? I mean, this
Maybe I can
Uh,
answer your kind of question. So basically, you have diffusion of superconducting order parameter from the left superconductor, from the right superconductor.
Okay, this psi is not the
Yeah, no, but
superconducting.
I'm saying on the left side.
That was maybe not clever to call it psi.
Quite new to this phenomenon. So you have presence of phase presence. On the left side, there is a global phase associated with superconducting order parameter. And then you have those two angles with index L and R. All right.
Yes, but I think the question was if I can give meaning to this factor.
No, the meaning
No.
I understand, but the meaning of those functions. I mean,
Then you're better than me because I don't understand the meaning of this factor in and of itself. It's really a mathematical observation that happened here.
I think this, no, look, this actually, we talk about this expression. For a bulk superconductor, you don't have this term, you have one. I remember from Fetter-Walecka book quite well. So this factor which you add is somehow maybe of heuristic approach or whatever, but it does include the superposition of phases from two superconducting. If you have two free leads, I would expect the phase of first lead, second, and the third. So you can probably even generalize this problem. So that's true.
Okay, thank you.
can you switch to this?
Yes. Okay, so
I need to understand.
Okay, but look, it will take time. So let's say, let us postpone for a discussion, right?
Yeah, okay.
Okay,
let's
thanks.
break.
Thanks.
Okay.
So do we have any more questions from the audience, from Zoom audience? All right, so let us thank the speaker again.
Thank you.
Okay, so we have unsure and